Good day, everyone. Today we will begin our study of electrostatics. Electrostatics is the branch of physics that deals with electric charges at rest. Although we cannot usually see electric charges, their effects are all around us, from lightning during a storm to static electricity that makes a paper stick to a comb. By the end of this lesson, you should understand how charges behave, how objects become charged, and how these concepts apply to everyday life. Here are the lesson objectives. First, explain the historical development of electrostatics. Next, describe the structure of atoms and electric charge. Differentiate positive, negative, and neutral objects. Explain how objects become electrically charged. Distinguish conductors from insulators. Use coulomb, ampere, and elementary charge in simple calculations. After these lessons, these objectives will guide our discussion today. Have you ever seen a $100 bill? Here is a $100 bill of the United States of America. You might be wondering why I am showing you a $100 bill. The person in this bill is Benjamin Franklin, one of the pioneers in the study of electricity. His experiments and ideas help shape our modern understanding of electric charges. Benjamin Franklin was not only a statesman and inventor, but also an important contributor to electrical science. He introduced the idea of positive and negative charges and proposed that electric charge is conserved. Interestingly, the labels positive and negative were simply names he assigned to two types of electric charge, and we still use them today. He is the inventor of the glass harmonica, bifocals, stove, the lightning rod, and he proposed the idea of that became the foundation of the law of conservation of charges. Of all the things that I've shown you in the previous slide, the lightning rod was especially important for this discussion. The lightning rod, as the name suggests, it captures lightning. But what did early people think about lightning? Before Franklin's time, many people believed lightning was a supernatural phenomenon. But Franklin proposed that lightning was actually electrical in nature. Through his famous kite experiment, he demonstrated that lightning and static electricity are related phenomena. Although the experiment was dangerous and should never be repeated, it helped establish a scientific study of electricity. We've mentioned the word electricity, but what's the origin of the word electricity? The word electricity comes from the Greek word electron, which means amber. Amber is that dried sap from a tree. Ancient Greeks noticed that amber attracted small objects after being rubbed. This simple observation was one of the earliest recorded examples of static electricity, especially by Thales of Miletus, also known as today the father of ancient Greek philosophy. William Gilbert expanded these early observations. He studied materials that behave like amber and introduced the term electrous, meaning like amber. Because of his work, he is often considered one of the founders of electrical charges. Sir Thomas Browne also first used the English word electricity in 1646, which was derived from Gilbert's earlier work, and this comes from the New Latin electricus, meaning like amber. The word electricity refers to a broad range of phenomena involving electrical charges. Electrostatics specifically focuses on charges at rest. In studying electrostatics, we are interested in electric charges, or the forces between them, electric fields, and how the charges behave in different materials. To understand electric charge, we first need to understand the atom. An atom is the basic unit of matter, and we've known that from our previous topics and courses. It contains three major subatomic particles. So what does the atom consist of? It contains protons, electrons, and neutrons. All atoms in the periodic table have an equal number of protons and electrons. All the elements in the periodic table are made of atoms. Although elements differ in the number of protons they contain, the basic structure remains the same. Understanding atoms helps us understand how electric charges originate. This table shows you the characteristics of each of the subatomic particles. We can see here that protons carry positive charges, neutrons have no charge, electrons carry negative charges. Protons and neutrons are located in the nucleus, while electrons move around the nucleus. The interaction between these subatomic particles, especially protons and electrons, is the basis of electrostatics. So what will happen if there is an imbalanced number of protons and electrons in an atom? Let's see how this happens using a simulation. I would like you to go to this site, and I want you to manipulate the number of atoms, the number of protons rather, and the neutrons and electrons of each atom that you can see in the build an atom model in the PhET Colorado Sims. This brings us to one of the most important concepts in electrostatics, electrical charge. Electrical charge is a fundamental physical property that causes objects to experience an attractive or repulsive force toward one another. And we know that there are two kinds of charges. We've said that in our introduction. These charges were named by Benjamin Franklin. Neutral atoms have equal number of protons and electrons. However, again, if an atom gains or loses electrons, it becomes charged. You've seen that when you manipulated the PhET Colorado Sims in the previous slide. This charged atom is now called ion. Let's see how this happens using, again, the simulation. I want you to go back to that simulation and explore further what happens when we add an electron or we take an electron from an atom. Now after that, let's explore the basic law governing charge interactions. In physics, we have what we call the charge law, one of the most important laws in electrostatics. According to this law, like charges repel each other while unlike charges attract each other. In other words, two positive charges repel and two negative charges repel, but a positive and a negative charge attract. But how do objects become charged in the first place? Objects, they can be charged electrostatically. Objects become charged when there is an imbalance between protons and electrons. Since protons are usually fixed in the nucleus, charging typically involves the movement of electrons from one object to another. Rather than just discussing the theory, let's observe electrostatics in action. So what happens when you run a plastic comb through your hair and then brought near a pile of paper scraps? I want you to get 10 to 15 paper scraps, approximately 0.5 by 0.5 centimeters in size, and a plastic comb and your hair. I want you to comb your hair for about 5 to 10 minutes, and after that, bring the comb closer to the paper scraps and observe what happens when two similar materials charged the same way come into contact. This time, I want you to, again, go to phetcolorado.edu, and we have a Sims there, and the title is Balloons and Static Electricity. I want you to manipulate the balloon and follow the instruction in the Sims. So what does this observation tell us? So what do you observe? What does the experiment imply? These experiments provide evidence that electrons are being transferred. Charging does not create new charges, And again, electrons are transferred from one object to another. Our understanding of charge improved through the work of many scientists. Let's take a microscopic view of charges. And we know that electric charges exist within atoms. In 1897, J.J. Thomson discovered that all materials contain light, negatively charged particles that he called electrons. Between 1909 and 1911, Ernest Rutherford, a student of Thomson from New Zealand, discovered that the atom is a massive, possibly charged nucleus. So the works of Thomson and Rutherford, they were very important, and they became the foundation of what we know about electric charges. An unequal number of protons and electrons again will result to charges. Positive charge is the resulting charge when an atom is missing one or more electrons. You can see here when a sodium atom releases one electron, there will be an imbalanced number of protons and electrons. There is a net charge of positive 1, and that's why a sodium atom becomes sodium ion. On the other hand, negative charges result when one or more freed electrons attach to an atom. In this case, a fluorine atom receives or gains one electron, and there is now an imbalanced number of protons and electrons, having now a negative net charge. Fluorine atom in the process becomes a fluorine ion. So, to summarize, a charged atom is called an ion. An atom with balanced number of protons and electrons has no charge. We call that neutral. If you notice, only electrons are gained or lost. For protons, it's difficult, and protons, they are not easily removed or gained by an atom. Only electrons. So if an atom or ion is positive, that means it has more protons than electrons, saying that electrons are removed from that atom. If an ion is negative, then it can be said that that ion has more electrons than protons, saying that um, that atom or that ion receive electrons. How did objects gain charges? From a microscopic point of view, acquiring charge is a process of transferring electrons, and we've been saying this since the previous slide. If you rub two different materials together, it produces electrostatic charges. Most objects are electrically neutral because they contain equal amounts of positive and negative charge. Some of the negative charges are transferred to the other material in the process, just like when you comb your hair or when you brought that comb near to uncharged materials, just like what you've done in the balloon experiments. So if electrons move from one object to another, what happens to the total charge? That question is answered by the law of conservation of charges. A basic rule of physics is that whenever something is charged, no electrons are created or destroyed. Electrons are simply transferred from one material to another. Therefore, charge is conserved. It's just like saying that when an object is charged, it simply means that there was a separation of positive and negative charges among its atoms. Again, we can say that charges are separated. And you have to take note that protons do not leave the atom, only the electrons. To check your understanding, what if you rub electrons to your feet while you walk across a rug? Are you negatively or positively charged? So if electrons are transferred to your body while walking on the carpet, your body gains excess electrons. Therefore, you become negatively charged. One example of this is the phenomenon of lightning. I want you to search in the internet about the topic how lightning forms. Lightning is a large scale of electrostatics. Inside, inside storm clouds, collisions separate positive and negative charges. When the electric field becomes strong enough, a sudden discharge occurs between the cloud and the ground, producing lightning. But you know that not all materials respond to charge in the same way. There are materials that we call insulators and conductors. Electrons of different types of atoms have different degrees of freedom to move around. We call that electron mobility. All materials may have either free or loose electrons or tight or fixed electrons. Free or loose electrons, they are unbound electrons and they are free to leave their respective atoms and they float around in the space between adjacent atoms. On the other hand, tight or fixed electrons are bound electrons that are not free to leave their atoms and they're mostly found in the innermost part of an atom. To differentiate between insulators and conductors, let's define each of these words. A material that allows charges to move about easily is called an electric conductor. So these materials have high electron mobility therefore, or we can say they have many free electrons. Examples of conductors are silver, brass, gold, aluminum, iron, steel, brass, bronze, mercury, graphite, dirty water, and concrete. Material through which a charge will not move easily is called an electric insulator. These materials have electrons that have very little freedom to move around. Examples are glass, rubber, oil, asphalt, porcelain, ceramic, quartz, cotton and paper, and wood if they are dry, plastic, air, diamond, and pure water. In this diagram, we can see here um, the different materials and their increasing ability to conduct electric charge. The more we go to the right, the more that a material will become a conductor. To our left, these materials are considered insulators. In between, these materials are considered semiconductors. We've talked about the air. So when will air become a conductor? We know that air is an insulator, but when will it become a conductor? The answer is only when it is ionized. And when will this happen? This happens during lightning when excess charges in the cloud and on the ground are great enough to remove electrons from the molecules in the air. That's a phenomenon called lightning because basically air is an insulator. However, under certain conditions, charges move through air as if it were a conductor. Remember the experiments about the plastic comb and the balloon? In that experiment, is plastic comb a conductor? How about the balloon? How do we know which objects acquire positive and negative charges? Or can we predict which material becomes positive or negative after rubbing? To answer that question, we have a diagram. We have a concept in physics called triboelectric series. A triboelectric series is a ranking of materials' ability to hold or give up electrons. Johann Carl Wilcke published the first triboelectric series in 1757 paper on static electric or static charges. In that diagram, a material towards the bottom of the series, when touched a material near the top of the series, will become a more negative charge. The series will tell us which objects acquire negative or positive when rubbed together. As we can see here in the diagram, materials at the top end tend to lose electrons and become positively charged, whereas materials at the bottom tend to gain electrons and become negatively charged. So a good rule of thumb is this: when two different materials are rubbed together, the materials higher in the series becomes positive and the material lower in the series becomes negative. Example, if you rub glass against an amber, since glass is on the top and amber is in the bottom, we can easily predict that glass will gain positive charges and amber gain negative charges. A better look on the triboelectric series is this diagram. We can see here, air is ranked number 1 in the triboelectric series, becoming more positive. And at the bottom of the series, rank 24 is Teflon. So we would easily expect or predict that Teflon will gain negative charges when rubbed against any of the materials in this list. To summarize, in conductive materials, the outer electrons in each atom can easily come or go and are free of and have free electrons. In insulating materials, the outer electrons are not so free to move. All metals are easily conductive, whereas most plastics are insulators. So far, we've described charge qualitatively. In the next video, let's measure the quantitative side of electrostatics.